Good morning everyone, and welcome to today's worked exam answer video. After a poll that I put on my Instagram story the other day, I am having a look today at a question that fulfills two of the briefs that students said that they wanted me to have a look at. One was required practicals and one was questions on year 12 content that you might get asked. Now, all of the required practicals, be them from year 12 or year 13, could appear on paper 3, where 40 marks of paper 3 is all practical questions, but this particular practical, which is required practical 2, could also appear on paper 2. Hello, kiddo. So I've chosen to have a look at this one, and it has a practical component on the front. So we've been given a bit of a method that we have to improve, and that's a levelled marker for 6 marks. And then on the back, we've got the associated calculation, and that is not quite such a straightforward one, so again I thought it would be useful to do. So the practicals can be built into more theoretical based questions on papers 1 and 2, as well as appearing on paper 3. So as always, I will do all my highlighting, annotating, worked answers, and then I'll come back and explain it all to you guys. Okie dokie, so the whole question is about enthalpy changes, and as I said, we've got the practical component and then we've got a more theoretical calculation component. Then it actually on the back does go back to a more practical question with regards to uncertainty. We'll work through each step. I might need to take a pause because heaven forbid I say something wrong a bit later in the video and have to start again, but I'm going to intend to do the questions on this page to start. So we've got part A, state the meaning of the term enthalpy change as applied to a chemical reaction. So that's a straight up definition that we need to be familiar with. So enthalpy change is the heat energy change under constant pressure. Definitions, while they don't come up all that often in year 13 papers, can still come up. I would suggest that enthalpy change is perhaps more of a year 12 definition, because this is a year 12 required practical from the energetics topic. This could also appear on an AS paper where the definitions are a little bit more common. Doesn't mean we shouldn't learn them though, because whilst in a year 13 paper you might be less likely to get, oh please define this for 2 marks, if you know the definitions, it means that you're going to understand a lot more the context, the understanding, the theory, the reasons for why different things are happening or how to draw cycles, etc. So it's definitely worth knowing your definitions. Now on to the chunky practical part. So we're told that a student determines the enthalpy change for the reaction between calcium carbonate and hydrochloric acid. We're given a balanced chemical equation, and then we're told that the student follows this method. They've measured out 50 centimetres cubed of a 1 mole per decimetre cubed aqueous hydrochloric acid using a measuring cylinder, and I drew a lovely yellow flag. And they pour the acid into a 100 centimetre cubed glass beaker. They weigh out 2.5 grams of solid calcium carbonate on a watch glass and tip the solid into the acid. They stir the mixture with a thermometer and record the maximum temperature reached. Now, that is a pretty shoddy method, but we obviously need to understand why and how to do it better. We're told the student then uses the data to determine a value for the enthalpy change, and we have to explain how the experimental method and the use of apparatus can be improved to provide more accurate data, and then describe how this data from the improved method can be used to determine an accurate value for the temperature change. So in my little answer, I've broken it up into 3 parts. It is a levelled marker, and these are what the 3 stages are broken down into in the mark scheme for this levelled question. So stage 1 is about the apparatus, stage 2 is about the method, and stage 3 is about the data. I've written the data in words. You can draw a sketch. You can get all of the points in stage 3 by drawing a sketch of the graph that I have explained in words. You could add a couple of labels and you would still be able to gain full credit for that. And I guess that applies to more than this question. If you feel that doing a sketch will help you to explain something, go for it, because you can often get marks awarded from diagrams, little sketches, illustrations, things like that. So don't be scared to do that. So the yellow flag, I should have thought about this and done this question in red. Measuring cylinders. I'm sat here shaking my head, not that you can see that, but please at A level do not ever say that we are going to be using a measuring cylinder. If you have a choice, do not pick a measuring cylinder. If they're telling you we're using a measuring cylinder, please question that. Please change it. A measuring cylinder is very imprecise, meaning the error on it is quite big. So when we think we've measured out, in this case, 50 centimetres cubed, we actually could be a fairly decent range either side of 50 centimetres cubed. So we want to use a more precise piece of equipment, and for 50 centimetres cubed, I would be using a burette. So I've swapped the measuring cylinder for a burette, which is a more precise piece of equipment, meaning it will have a smaller absolute error. The other thing that we needed to pick up on here is a glass beaker. If we're trying to measure the maximum temperature reached and we're using a glass beaker that's going to conduct some of that heat into it, we're not going to get a very accurate value. So we want to be doing this in a polystyrene cup because it is a better insulator, and then we could also add a lid to try and minimise the heat loss even further. The other thing that they haven't done here, which I think is less important, but I did also mention, is they've weighed out the 2.5 grams of the solid calcium carbonate on a watch glass and tipped the solid into the acid, but they haven't reweighed the watch glass. We should always be weighing by difference, i.e. weigh the watch glass, the weighing boat, whatever it might be, with the solid on it. Prior to tipping the solid out, you should always go back and reweigh the watch glass or the weighing boat so that you know the exact mass of the solid that you have added, in this case calcium carbonate. So we have to be doing that as well. Now the other glaring error here is that they never actually took a value for the initial temperature. They just threw the solid in and then, stirred it, recorded the maximum temperature reached. How can you get an accurate temperature change if you don't know what the temperature was in the beginning? You can't. But the method needs to be tweaked a little bit more significantly than that. So with this required practical, what I hope that you all did at your schools and colleges is you got your polystyrene cup, you added the solution to the polystyrene cup, and you measured the temperature of that solution in the polystyrene cup on its own every minute for 3 minutes. Then at the 4th minute, the point of mixing, you then add the solid into the same cup as, in this case, the acid. And you don't take the temperature at the 4th minute, you just add all the solid in and then go back to your stirring, make sure you've got your lid on there, keep everything as samey as you can. Then we would be measuring the temperature every minute after the 4th minute for a further 10 to 15 minutes. So from minute 5 to minute 15 or minute 20. And the reason why we do this is to allow for the fact that not all of the heat will be generated in this reaction immediately. So we don't kind of add the solid and get a sudden, ooh, wow, it's reached maximum temperature in the first 5 seconds. It doesn't do that. It takes a little while to generate all the heat. But also, because it's an exothermic reaction and heat is being given out, it will always be cooling back to the temperature of the room. So we have to take that into consideration as well. That's where the data analysis bit comes in. So we're going to plot a graph of time on the x-axis versus temperature on the y-axis, and we're going to plot all of the data points. So from 0 to 3 minutes, and then from 5 to either 15 or 20. You will have a gap at the 4th minute because we didn't take a temperature at the 4th minute. So for the first 0 to 3 minutes, you will then draw one line of best fit, which you will extrapolate to the 4th minute. You will then plot a line of best fit for minutes 5 to 15 or 5 to 20, and you will extrapolate that line back to the 4th minute. And then you will have at the 4th minute 2 points, one from your original temperature line of best fit, one from your end temperature line of best fit, and then you are going to measure the difference between those 2 points at the 4th minute, and that will give us the most accurate temperature change possible. That is a pretty standard method. I've seen other questions nigh on identical to this where they've asked similar things in terms of how can you tweak the apparatus, how can the method be improved, and how would you analyse the data. So it's definitely a good one to know from a method point of view, this particular required practical. Others, the methods are less important, but this is not one of them. So for required practical 2, certainly when we're thinking about the polystyrene cup, adding 2 substances into the same cup, we should definitely be using this for our method. So that's the first part. I'm going to turn over, take a quick breather, and then I will explain the calculation. Okay, so the calculation is about a different reaction, different experiment, but we are using the same concept. We're using a polystyrene cup. This time we're not adding an acid to a solid, so calcium carbonate. This time we're doing neutralization, and we're adding an acid to an alkali, or an acid and an alkali inside of a polystyrene cup. We're told how much hydrochloric acid and how much sodium hydroxide has been added. So for both of them, it's 50 centimetres cubed of a 0.5 mole per decimetre cubed solution. And we're told the enthalpy change for this reaction. So I guess the more basic version of this question is they'll give you the change in temperature, they'll give you the volumes of things that you're adding together, they'll give you the specific heat capacity, you'll work out Q, then you'll use Q in the moles to work out the enthalpy change. However, here we've been given the enthalpy change. It's minus 57.1 kilojoules per mole. We're actually trying to calculate the maximum final temperature reached. The initial was 18.5. We want to find the maximum final temperature. We're told to assume the specific heat capacity is 4.18 joules per Kelvin per gram, and we've got to assume that the density of the reaction mixture is the same as water and is 1 gram per centimetre cubed. So a couple of things that I just annotated around the question. I converted my volume into decimeters cubed because I'm going to need that for doing the moles, and because we've got the same volume and the same concentration for both the sodium hydroxide and the hydrochloric acid, we're going to get the same moles for each. The ratio is 1:1, so neither of them is in excess, neither of them is limiting, so we can just use the moles of either of them in our calculation. Because the density we're assuming is 1 gram per centimetre cubed, this is the bit that's different with neutralisation. Because we've got 2 solutions going into the cup, the temperature change that we measure is going to be based on the total volume, so 50 of the HCl and 50 of the NaOH, so the total volume is 100 centimetres cubed, which is equivalent to 100 grams. And then the other thing that I wrote on here is that the negative sign tells us that this is exothermic, so therefore the final temperature needs to be greater than the initial temperature, and it does say the maximum final temperature here as well, as another clue that we should be getting a final answer that's bigger than the initial. But the other thing to say with that negative there is if we think about doing these calculations forwards, so using MC delta T to get Q, using Q in moles to get delta H, those numbers always come out as positive on the calculator, and in calorimetry experiments we have to decide whether the reaction is exo or endothermic, and if it's exothermic, like this one clearly is, we manually have to make delta H be negative. So when it comes to doing the calculation, because that's just an arbitrary negative sign that we have stuck in front of that number, you don't need to take the negative part forward into the calculation. So I'm just going to use 57.1. because every single value of Q is always going to be positive. So that would suggest every single value for delta H will be positive, and thus every reaction is endothermic, which it's obviously not. We then manually say, oh, no, it's exothermic, I'll make it minus 57.1. But in our calculation, we can start with 57.1 because that is what we would end up with if we were working forwards. So the 2 equations that I've already alluded to, Q is MC delta T, and delta H is Q divided by moles. So if we want to get delta T, we're going to have to rearrange that to be Q divided by MC. Therefore, we first of all need to get Q. So rearranging the delta H equation, Q is going to be equal to delta H times by the moles. So delta H we've said is 57.1. The moles is the volume of 0.05 times concentration of 0.5, which gives me 0.025. And I've multiplied those together, and that gives me a value for Q in kilojoules, because the units of delta H are kilojoules per mole. Now again, if we were doing this calculation in the forwards direction, you'd get your value for Q, that would be in joules, you'd then divide it by 1,000 to get it in kilojoules. We now have our value for Q in kilojoules, and we therefore need to do the opposite and times it by 1,000 now to get it into joules, which I've done, 1,427.5 joules. Then I can sub that in alongside the mass, which we've already discussed is the 2 lots of 50 centimetres cubed added together, so 100 centimetres cubed and thus 100 grams, and the specific heat capacity, which is 4.18. When I put that in my calculator, I get a temperature change of 3.42. So if I knew the initial was 18.5 and the difference was 3.42, if I did 18.5 add 3.42, I should get the maximum temperature reached, the final temperature, which I get to be 21.9 degrees. And that's my final answer. Now that gets you 5 marks for doing the calculation backwards, where you're probably only looking at getting 3 for doing it forwards. Even though the steps are the same, just obviously reversed, you are getting more marks here. And that would be, I guess, a tip for questions you're used to doing one way, so to get delta H. If you then get asked to do it in reverse, first of all, try and think about how you would do it usually. Maybe make a note of all the steps you'd do, so you'd get the mass of the substance that's getting either warmer or colder, warmer in this case, get the temperature change, and then you sub those in to get Q. Then you'd divide Q by 1,000, then you'd figure out the moles and do Q divided by the moles. So then we just need to do everything in the reverse order. Okay? And then the little practical question at the end, suggest how, without changing the apparatus, the experiment in part C could be improved to reduce the percentage uncertainty in the temperature change. Now this question can come up with regards to any practical at all, but I do think it comes up quite a bit in required practical too, because there's quite a few different types of measurements that we're making, and in this case it's alluding to the temperature change. Now when we are calculating percentage uncertainty, this is our equation. So the absolute error on the piece of equipment divided by the measured value times 100 will give you the percentage uncertainty. Now they've told us that we're not allowed to change the apparatus. If we were, we would choose a more precise piece of equipment because the absolute error on the top of the fraction would be smaller, and that would then reduce the percentage uncertainty. However, the absolute error's got to stay the same because we can't change the apparatus, and the only other way therefore to change the percentage uncertainty from this calculation is to change the measured value. So in this case, the temperature change in the experiment needs to be different. So if I need to increase the size of the temperature change in order to bring the percentage uncertainty down, which I do, if I have a bigger number on the bottom of the fraction, it's going to make my answer here smaller. So we need to increase the size of the temperature change. You then have to link it back to the specific method. So in this case, what we're measuring the temperature change of? We're measuring the temperature change of the sodium hydroxide and the hydrochloric acid solution in the polystyrene cup. How can we therefore increase the size of the temperature change? Well, the most obvious route is to reduce the total volume of the solution. Using 50 centimetres cubed of both acid and alkali is quite a lot. 100 centimetres cubed is a big volume, i.e. a big mass, for us to have to heat up. So if we were to halve those volumes and only use 25 centimetres cubed of each, then we would experience a greater temperature change in the solution based on the heat that's generated. And in that experiment, it only went up by 3.42 degrees, which is very, very small. And that would therefore give us quite a big error if we plugged in the error on the thermometer divided by 3.42 times 100. So we always want the biggest measured values possible, so that we get the smallest errors possible. Like I say, that comes up in relation to all sorts of practicals. The answer will always be the same in the first instance of you need to increase the measured value on the bottom of the fraction. The difference between different practicals will be how you go about doing that. So if it was a titration and you had a mean titer on the bottom of here, to increase the mean titer, you're going to have to change the concentration of what is actually in the biuret. So to increase the mean titer, you would decrease the concentration of what's in the biuret, for example. But But yeah, so that's quite a long 13 mark, both practical and theoretical question on energetics. Not the nicest, because you've obviously got this 5 mark calculation, as well as the 6 mark practical part. But hopefully all of that makes some sort of sense. But if anybody needs any help with this particular practical or any of the practicals, maybe how to revise for them, what the key parts are, then please just drop me a comment. Thanks so much for watching, guys.